Good morning, good evening to everybody. It's a big pleasure to be with all Poultry School audience again in another webinar. We have a big honor today again. We were sharing with our audience, we're excited about this collaboration with the Experimental Poultry Centre in Belgium. And today we have Tom Van Hertem. He's a researcher in the Experimental Center, and he's working with sensors, data technology, and we can say he's an expert in ammonia. And so we're going to be talking about gas emission, specifically ammonia, an update of the situation and research that they are doing in the Experimental Center. So Tom, thank you very much for your time, for your willingness to share information with our audience and aligning with our vision in Poultry School of putting information in an accessible way for the industry. So as always, this is going to be recorded and then it will be accessible in our platforms. It's going to be like a 45, 50 minutes presentation. And then if you guys have a question, we will have 10, 15 minutes. So Tom, the time is yours and thank you very much.
Yes, thank you very much, Rodolfo, for the introduction. So hello, everybody. My name is Tom Van Hertem, a researcher at Experimental Poultry Centre. And here you see in the first slide an overview, a bird's eye view of our facilities. I will talk to you today about the situation and the research that we're doing on ammonia emissions. We do it for layers and broilers as well. But before I go into detail, let me introduce myself even further, because my career didn't start there at the Experimental Poultry Centre. Actually, I grew up at a small dairy farm in Belgium. We have around 60 cows, so we have a small family farm. And also my education ended up there. So I started working on automatic lameness detection in dairy cattle. So what we try to do is to record the gait of the cows while they were walking and try to automate the gait scoring in order to assess lameness in the dairy cows. After that, I quit the scientific world, let's say, and I started working in the commercial farms, the first commercial settings. The first one was Fancom. I started working there in 2015. I joined there the research team, and there I was working on camera technologies in order to monitor bird behavior in relation to control of climate control systems. One of the systems I worked on was the dynamic system, as you can see there, where we were able to score the activity and the distribution of the birds in the house. After that, I joined Hato Lighting, which is a lighting company for agriculture, so for livestock. And their LED lighting was one of the main products. And there I joined the research team to evaluate the effects of lighting on bird behavior, for instance. Besides my career, I also am a father of 3 kids. So my oldest daughter is 9. I have a son of 7 and a daughter of 5. And we grew up together now at the family farm, as you can see there. I'm not a farmer myself, but my brother is, but I'm still living at the farm. So I'm still linked to the dairy sector as well. Okay, what I will present to you today is we go into the facilities that we have at the Experimental Poultry Centre. I will talk to you more about the monitoring of ammonia emissions. We also evaluated some measures and techniques to reduce the ammonia emissions, and also the struggle of balancing welfare and emissions in the poultry sector. So let me first go to our facilities. You already saw the picture in the first slide, but let's go more into detail. So here you see the picture again. On the left side, you see the one big roof. That's our layer house where we have 30,000 hens. And on the right side, you see the 3 smaller buildings where we have 3 houses where we can house in total 42,000 broilers. So we can say we are a quite large experimental facility. But we're not just a regular research facility. We are doing the research on semi-commercial scale, which means that we sell our products like the meat The broiler chicks and the eggs, we sell that to the commercial market. So that also means that we have to apply to all the constraints that all the farmers has to agree to. We also have our pens are not small. We house them in at least 1,000 birds per pen, let's say. Our research is focused on applied research. So we want to develop or test solutions that help the farmer, the poultry farmer in Belgium or in Europe. And we also look at the 360 approach. So we don't only try to solve one problem, but we also want to make a workable solution for the farmer so he can implement it in the field. But of course, we're still in an experimental setting, so we need trials and repetitions. So that's why we have smaller pens and a lot of repetitions for that. And we have that for the broilers and the layers as well. If we then look at the broiler sheds, we have the older one, let's say, that were built in 1993. So they are 4 different compartments with floor housing for the broilers. And each house is divided in 4 smaller pens where we can house 1,500 broilers. The ventilation concept here is that the air is coming from the side through the air inlets and leaves the shed in the ridge through the ventilation fans that are installed there. It's a quite old setup, but it's most transferable to the poultry sector in Flanders. Then in 2013, we built a newer shed. It's a different approach here where we have 8 identical pens of compartments. Each compartment is divided in 2 pens and each compartment is 112 square meters. And we can house 2,300 broilers there per compartment. We have here central heating with hot water pipes. As you can see in the pictures, you see there the gray pipes on the sides of in the house. That's how we can heat up the sheds here. And we have the air is coming in from, in the top view picture on the left, the air is coming in from the bottom of the picture and is going out of the compartments at the top. And there it leaves the shed. So there we have a kind of length ventilation there that we have there. If we then look at the layer house, we have there 30,000 laying hens, but they're all divided in 12 different compartments. And these compartments, we have 4 different housing systems. We have enriched cages, still 3 compartments. We have 4 aviary types with wide alleyways. We have 4 aviary types with more narrow corridors and a big Dutchman system. And we also have 1 prototype setup of the Veranda Code 2 Plus system, which is a system developed by Vancomatic. They're all under the same roof and they're located next to each other. So we have 12 compartments with a few thousand animals per compartment in the building. So that are the facilities that we use and in order to perform our research. That we also, like I said before, we want to look at the 360 degrees approach because we want to integrate solutions and tackle multiple questions at the same time. For instance, we are looking at emissions, but also look at the energy, the housing system, or the automation of the system. All in all, we try to find a solution that brings together the animal, the human, and the environment together to find the ideal solution for all 3 parties in this question. Now, one of the main reasons, or one of the hot topics now at the moment, is a nitrogen situation in Flanders. I try to explain it now. First of all, the European Union, they have proposed that we should take action to avoid further deterioration of our nature in Europe. Flanders has reacted to that to avoid even more nitrogen deposition on the nature. As you can see in the top picture, the nature areas that are designated nature areas in Flanders, they're quite scattered in Belgium. So there are not big nature reserves existing in Belgium, they're rather small, which also means that they are spread over the country, but also all very close to neighboring farms. So that's why a lot of farms are hit by the measures that are taken now. How do you want to avoid deposition? Deposition is the consequence of the emissions. The emissions come from one part from the industry and traffic that are mainly NOx emissions. And the other side, you have the agriculture that is responsible for the ammonia emissions. So they both arise, they concentrate in the air, and then they can deposit the nitrogen on the forest, the heathlands, the ponds that are in the nature reserves present. So ammonia emissions are the largest in the livestock sector. That's why the ministers, the government has asked to take action in the agricultural sector. And one of the actions that they require is that non-ammonia emission reduction compliant farms need to reduce their emission by 60%. They take the reference year of 2021, and they expect that we, the sector, comply to it by the year of 2030. So we have now still 5 years to comply to the new rulings. So we need solutions for that. First, let me go into a little bit of background. Is how is ammonia formed in the poultry sheds? First of all, it starts with the nitrogen intake of the birds. The birds need nitrogen in order to grow and to produce either meat or eggs. But of course, not all the nitrogen that they take in is being processed. So there's excess nitrogen because we don't do like precision feeding. With phase feeding in broilers, for instance, we can resolve this a little bit, but there's always some excess nitrogen available in the litter. When it's there's through a part is the nitrogen is part of the feces, but also from the uric acid. That's the main component of the nitrogen in the litter. The conversion from nitrogen to ammonia is through two processes. And those processes are influenced by the nitrogen content in the litter, the moisture, the temperature, the oxygen level in the litter, the surface area of the litter, the airspeed, the pH, the looseness of the litter, and the bedding depth. So you can see there are quite a lot of influential factors in the conversion process of nitrogen to ammonia in the litter. This is maybe also a good thing because it means that we can take a lot of actions to inhibit this process. Now, the government has already approved several reducing techniques that farmers can apply. So if they apply one of these rules, these techniques, they are complying to the regulations that they have set. But if you look in more detail in the regulations, you can see that most of them are related to housing systems. So if you build a new housing system, you can choose one of the systems in the list, and you then comply to the new rules. But if you have an existing housing system, you want to do actions on an existing farm, you are more related to management practices, and then there are only two defined at the moment. So this is actually one of the issues now, that the choice of the mode of action is now quite limited for the farmers who have existing buildings. And that's why one of the research projects that we started 2 years ago, it's called the Rambo. It's a consortium of Dutch and Belgian partners that we try to solve this issue. So we want to set up some research and to test and demonstrate different measures at different locations. We also want to focus on how to measure and monitor the ammonia and other emissions at the farms. And we also want to evaluate the reduction potential of the measures and techniques. We also want to go into discussion with the farmer, so with the government and with the general public. So we organize different activities like Tour de Boer. That means that we visit some farmers who have implemented a new technology, so we can learn from each other. It's more like a peer-to-peer learning process. We organize workshops and study events, and we also started individual advice trajectories with individual farmers in order to solve their individual cases. Yeah, one of the aspects was the monitoring. So let me now go into detail about the ammonia emission monitoring, how we do that at our farm at the moment. So because ammonia emission is actually two things are quite important there. First of all, you have the concentration of ammonia in the air, but also the ventilation rate, because you need to know how much air is going through your building. So in order to know the emissions, you need to measure both of these variables. In the introduction slides, you saw that we have 3 different types of buildings. So in our current setup, we also chose 3 different measures of measuring techniques to measure the concentration of ammonia in the houses. So first of all, in our newest broiler shed, we chose for a gas analyzer system. This is a Fourier transform infrared spectroscopy sensor. It's a quite expensive system, let's say, but it's a very accurate and it's a very accurate system. We work with it already for 5 years now, and we can not only measure ammonia, but also CO2, methane, nitrous oxide, and water vapor in this with the sensor. So we can measure multiple gases at the same time. How does it work is that this system is a central place and it's a gas analyzer. It means that we need to bring the air from the compartments to the analyzer. So we have air ducts from each compartment leading towards this gas analyzer. Now, in order to make it work, we have to prevent that water is entering the air ducts. So that means that all the air ducts are heated. And actually, in the last part of the sensor, the air is heated to 180 degrees. This means that there's a large energy cost in the use of this sensor. That's why it's not very favorable to use this in other houses at our site. And that's why we chose in the other houses for other sensor techniques. At the old buildings, we chose for a Dreger Polytron sensor. It's a more passive sensor. You hang it in the compartment, and then you can log a 1 to 10 volt signal that is related to the concentration of ammonia in the shed. It's an electrochemical component that you need to replace every year or every 1.5 years in order to avoid sensor drift and to maintain accuracy, but it's a quite accurate sensor. We installed one sensor in each compartment in our barn, and we located it in the middle of the barn, close to the 2 main exhaust fans that are always working. Then in our layer house, we chose a similar setup to the first. So we also chose there a gas analyzer because all the compartments are under the same roof. But there we used an X-Etris sensor. It's a different sensor method, but the approach is the same. So as you can see there in the left bottom, it's a box where there are valves, and there's a PLC that controls the valves and directs the air from the correct compartment to the sensor. So as you can see in the right bottom in the graph, you see they're different color. Every color is a different compartment. So we measure here the concentrations in sequence from each compartment. So it means that we cannot measure the gas concentrations at the same time in every compartment. We can measure it in sequence. And this sensor is limited only to ammonia, and we have a different sensor there for CO2, but the other, like nitrous oxide and methane, we cannot measure there. Now, all these sensors, they're good, but they also need quite a few calibrations. We do that together with a Flemish partner, Ilvo. They're more experienced at this part. So they do the calibration measures twice per year. So what they do is that they give like a known concentration to the sensor, and then they measure the output signal of the sensor. And that way we can relate the recordings to the truth value. And you can develop a calibration curve. Also for the ventilation, we need some calibration. You can measure the calibration with a measuring fan or with this with a measuring fan, but also then you need a calibration setup, and that's what you see here. You see there are 2 extra measuring fans that are installed on the exhaust fan, and through the rotation speed of the measuring fan, we can calibrate then the flow rate. Okay, so that's how we measure the ammonia emissions at our facilities. I showed you 3 different ways, but the principle is the same. So we measure the concentration through one sensor method, and we measure the ventilation rate. Now, when we have which means that we can now measure the ammonia emission, and that also means that the next step is that we can now see what are now the desired measures to reduce the output. And in this Rambo project, we proposed a few techniques and measures for poultry. First of all, were some bedding materials that we use in the poultry sheds, in broilers or in layer hens. Another was the litter removal frequency. So the litter, the broilers and the manure and the litter get mixed, and then ammonia is produced. So it would be better if you can remove that litter during the presence of the birds. But of course, it's very difficult to remove it when the birds are there. So we need to find a solution and have to evaluate what is the benefit that we can get there. Another is the use of zeolite additives that we can use either in the feed as an additive or in the bedding material as in the litter. Another is in the layer hens, then the manure belt. So there are manure belts in the system, especially in the cages, but also in the aviary system. There are some manure belts there. What is the influence of the frequency of this extraction? If we do it daily or weekly, what is then the influence? Now, first, what we also have in our shed is that we have the 4 different housing systems. So we have the enriched cages, we have the aviary types, and we have the Veranda Code 2 Plus system, which is the prototype setup. Now, during 1 month in summertime, we did an initial recording of the emission in those different housing systems. And here I represented the different ammonia levels. So there's the concentrations, and I put the aviary system with 2 rows as the standard, that's 100. So the others are related to that. And there you can see that the 2 aviary systems are quite similar, but the cage system, which is the red line, is around 30% of the emission that we have in the aviary system. If we look at the Code 2 Plus system, the prototype, we see that's around the 40% during summer. So you see here that the cage system has around 30% lower emissions than the aviary system. What we have to consider here, why is this important, is that Europe has put a ban on enriched cage housing. So Flanders will implement this new ruling from 2036. So that means that all the enriched cages will be banned in 10 years time from now. And that the farmers that are now working with enriched cages have to find a solution for that system. So either they have to go to aviary housing or have to define another system, let's say. Also the prototype system, which is like an intermediate form between aviary housing and enriched caging, seems promising in terms of ammonia emission. A previous study already evaluated the welfare of the birds in that system, and there they found a strong correlation with the welfare that the birds show in aviary systems. So in that sense, you see quite some similarities there. The previous slide was only 1 month in summer. We extended the period now. So we started in summer and we did it now till April, which was the end of the flock. So now the poultry house is empty. Here you can see now that the emissions of the green line, which is the aviary housing, were still very much higher than the ones in the cage and the prototype housing. If you look at the numbers, you see there are quite difference, almost 10 times higher on average, which is quite a big difference. And then, so also we have to think about in 2030, 2036, we need to get rid of these enriched cages. We have to go to other housing systems, but then we have to consider that we will increase our ammonia output probably. Next measure that we took was the manure belt extraction for layers. So what we did was set up a small trial there, is that for one part of the system, for the houses, it was an enriched cage housing, we did 1 time per week on a Friday with the manure removal, or we did it 3 times per week on Monday, Wednesday, and Friday. And we swapped the trial in a crossover, so then we switched the compartments. What you can see is quite large differences between the trials. So that means that it seems to be working. And if you look at the actual numbers, you see you can have a reduction potential of 60 to 75% even. So there seems to be an effect, is the more frequent you remove the litter from the house, you can reduce the emissions there. If you then compare here, so we did it in 2 different compartments. So that are the different color bars, but look mainly at here the frequency of the removal. If we did 1 time, you were around 200 grams per day. If you do 2 times, you're at 120 grams per day. And 3 times per week, you're at, let's say, 60, 70%, 70 grams per day. So this shows that the more frequent you remove the manure from the house, you get lower emissions, which is very promising. Another thing was the effect of zeolites in the feed or in the litter. Zeolite, what is zeolite? I don't know if you know this compound, but it's a group of microporous crystalline silicate minerals. So you can find them, they're like small rocks that are crushed. And they're usually used as adsorbents or catalysts. So they are used in industry, they're often used as catalysts to facilitate some processes. And they're known to adsorb the ammonia components. So that's, in theory, it should work like that. But yeah, we did some trials. And as you can see here, for instance, the top one, we did an application of zeolites in the litter. We applied it 5 to 6 times, each time 150 grams. And in the end, we got higher ammonia emissions instead of lower. So it had an adverse effect. We also applied it 1 time, so the same amount, but then 1 time on day 8, and then we got a reduction. So then we got 15% lower. So this shows that the mode of application can be quite important, how you apply the zeolites. One of the reasons why the frequent application got higher emissions is probably because the litter was more loose, was drier, and that's why probably we got higher emissions. It's also one thing we saw in most trials is that the litter was drier and looser when we applied zeolites. So it has a positive effect on litter quality, but it seems to be negative on ammonia emissions. If we then look at the broilers, first of all, what you see here is the common or general pattern that you see in broilers. So they live from 0 to 40 days. And you see the peak in concentration in the house is around week 3. So day 20, let's say, we have the peak ammonia concentration in the broiler shed. That's because then the ventilation rate is not maximal yet. So the concentrations can build up. After that, you increase the ventilation rate a lot, and then the concentrations go down. What you also see is there's quite some variation between the sheds. So we have 8 different sheds. We measure the concentration, and you see there's quite some variability. So that shows that there's some possibilities to reduce the outputs. So a first trial that we did is that we tested different bedding materials and feed compositions. So here you see again the pattern. The general pattern is the peak at day 20. And then what you see here is the control was the red box, that are the lines there that are used with straw pellets. The other is with reduced protein intake. And the bottom one are the flax. So we use flax bedding material there instead of straw. And then we saw a large reduction. So what we can see is that the flax bedding resulted in a reduced peak emission, and the reduced protein intake got also a lower peak, but they got higher at the end. So cumulative, there was not really a benefit of reduced protein intake. For the flax, we can say that we have a reduction of 25% of ammonia emission. So the bedding material or the bedding type can be influential on the ammonia production in your house. Another repetition is that we did there is, so you see the same pattern again in broilers. Day 20, you have the peak in emission, or not in concentration. The yellow line is with pulverized flax bedding. Also there we saw again a reduction, so we got a repetition of that. Another trial that we did is with the blue line here is with acidification of straw pellets. So there was straw pellets they were coated with some acid, but in the end we didn't see any benefit there in ammonia reduction. So that doesn't seem to work. It's also nice to know if something doesn't work, then we don't give farmers false hope. So that's also one of the reasons that we do the research. Now, the acidification of straw, we didn't stop there at the first product. We also tested another product that was more strongly acidified. So it was, the product used was sodium bisulfate. Oh, okay, first. What you see here is the blue lines is the control group. You see here again, the peak is around day 20, and then it stabilizes. With the acidification of the straw, we see that the peak is more delayed and more towards the end. So that's a good sign. And also the peak is lower. So in the end, we got here a very big reduction of ammonia emissions. We even got to 75% in the end. So how does it work? We also looked at the pH in the litter, and we saw there a very strong reduction of the pH. So we know that if the pH stays below 7, that then the formation of ammonia is inhibited quite strongly. And that's also what we see here. So this seems to be working very effectively in broilers, this litter material. Now, what we did up till now was that we measured the ammonia emissions of different measures and techniques, is just to show the potential of each of these measures. So it is research done that gives some indicative results, but this is not an official recognition of the technique or the measure. In order to do that, we now started a new project that will follow the official pathway of to get the measures recognized by the government. So what is the pathway there is that first you need to develop a plan. How do you going to measure it? How do you going to apply it? So you need to define a predefined protocol. And for pig and poultry farms with mechanical ventilation, this is quite well described. So we know what to do there. But it requires a 1-year continuous measurement in the same house. And we also need to do some additional reference measurements there to put it next to the 1-year continuous measurements. And we also have to do these measurements in 4 independent locations or in 2 case control settings. So doing the research only at our farm is not sufficient to get it recognized. We need to also find other locations there to test it and measure it. Now, when we have developed a plan, you need to put it in front of a scientific committee. They will validate the science behind it, determine the mode of action, see if it can work and will work. They will evaluate that and they will give an advice. This advice will go to the administrative team. They will check if all the requirements are met, and they will see if the farmer is using this technology, this technique, or this measure. How can we guarantee that it has been applied? So that's also one of the big problems, is that for some measures, it might work, but you also need to find a way how to prove it that you use this measure. So that's what the administrative team is focusing on. And in the end, it's actually the Minister of Environment that takes the decision, that gives the official grant. So the scientific committee and the administrative team, they only give advices that the Minister of Environment, he will make the final call. So this is the official pathway that we need to follow now. As you can see, it takes a lot of time because you need at least 1 year of measurements. There are also some feedback loops in this pathway between the scientific committee and the planning, and the administrative team and the planning. So it will probably take a year, or more than a year, in order to get techniques and measures recognized in Flanders. Now, why is this also important? Because we also look at the 360 degrees approach. So, and one of the issues there is that the poultry farmers are asked to balance welfare and emissions. So not only focus on emissions, but also there are some welfare constraints also popping up. One of the clear examples there is the introduction of the Better Chicken Commitment. I'm not sure if you're familiar with it, but that's some of the retailers in Flanders have exclaimed that they will, from next year on, 2026, they want to comply with the Better Chicken Commitment. What does it mean is that they want to allow only a maximum stocking density of 30 kilograms per square meter instead of the regular 42 kilograms. Thinning should be limited to 1 time per flock or even avoided. They also want to propose slower growing breeds instead of the conventional. This actually means conventional birds, they grow till 40 to 42 days old, let's say. But the slower growing breeds, they do at least 1 week longer, so 49 to 56 days of age, and then they get slaughtered. So we need 1 or 2 weeks extra in the production process. Also in the stable, there's some extra requirements. For instance, at least 50 lux of natural daylight, at least 2 meters of perches and packing substrates, and also the air quality should be monitored. And that's related to ammonia, and CO2 levels should not be over certain limits. There's also one retailer that also wants to introduce on-farm hatching in order to improve animal welfare even further. Now these commitments, let's say, for in the Better Chicken Commitment, we see that they have a very well-known effect on the welfare of the birds. But our question was, what about the effects on ammonia emission? That is not mentioned in this. What are the effects on animal welfare in practice? Because it's nice on paper, but how will it evolve in practice? And what is the effect on production results? If you have to reduce your stocking density and longer lasting rearing periods, what is then your effect on the production performance? So in order to answer these 3 questions, we set up different trials. So one trial setup was that we have the 8 compartments. We have there 8 pens with conventional broilers and 8 pens with slow growing broilers. So 4 of them were, half of them were like a conventional setup with 42 kilograms per square meter, and the others were 30 grams, so lower stocking density. To give you an idea, the 42 kilograms per square meter means that from the placement of the birds, you do like 21 birds per square meter, and with the 30 kilograms per square meter, it's around 15 birds per square meter. So there's a difference of 6 birds per square meter, which is quite a lot. If you see 6 to 15 birds, it's almost 1/3 of the birds less. Now, ammonia emissions, they were measured through the FTR method, the gas analyzer that measures ammonia, CO2, methane, nitrous oxide, and water vapor. Now, look at the results. So first of all, let me show you to the production results. What we see here is the slow-growing birds here. In the second trial, for instance, the feed intake was quite higher, as you can see. You have here around 3.8 for the conventional birds compared to 4.3 for the slow-growing birds. The difference between stocking density is not so clear in the second trial. Feed conversion is related to that, also quite different. So it's 1.46 for conventional birds compared to 166. So it's 0.2 kilogram, 200 grams of feed more for the same amount of meat, let's say. Stocking density had a small effect, as you can see here in the first trial, not in the second. But all in all, the end weight of the birds was the same. Even though they took longer time, they reached the same end weight of the birds. So production-wise, there we don't see a lot of differences. Yeah, maybe they consume more. Yeah, they consume more feed. But what about the ammonia emissions? If we then look here, is that we see here. So the H is on the x-axis. Here you see the red line is the conventional bird at 42, so high stocking density. Of course, as expected, we see there the first initial rise in ammonia emission there in that group, because they're highly density, a lot of birds there per square meter. We see there a lot of ammonia emissions arise in the beginning at around day 20. The other groups, they have a delayed increase. Also here, the conventional birds at 30 kilograms, lower stocking density, in the end, they go up very steeply. Now they get slaughtered at day 40, so then the emissions stop there. The house is cleaned, the manure is getting out, so there are no more emissions from that day on. But the other birds, they're still staying there 1 week longer. And then that's when we see a large peak in emissions still arising there. So the final week, we see almost a doubling of the emissions there in the final week. That was the first trial. The second trial, we see a similar thing popping up. So also there, the final week, we see there still a lot of emissions, high output of emissions at that period. If you then compare it, and then if you then compare the conventional setup, which is a high stocking density with conventional birds, and compare it to the slow growing birds at low stocking density, the new concept that I want to introduce, we see there that we have almost, we double the ammonia emission in the new concept. In the first trial, in the second trial, it was even 3 times higher. So this doesn't seem very favorable given the situation in Flanders, where we have to reduce the ammonia emissions. We also repeated this third and fourth time, and there we got similar results. So 4 times in a row, we did this trial and we got similar results, that we have at least 2 times, maybe even sometimes 3 times higher emissions when we have a slow growing breed and lower stocking densities. Now, what are the possible causes for this? Because we see it happen. What is probably the cause? First of all, the litter structure was quite different. Here you see a picture of the litter structure in the conventional broilers. You see it's very, what is the name? Clustered together. It's like a pancake, let's say. So it gets airtight, which means that the ammonia is not able to evaporate from the litter. Also, in the slow growing breeds, you have the looser litter, more drier, which means the birds can more scatter around, and also, this will probably evaporize the ammonia even more. You have the longer production cycles, so you have 1 week longer, so 1 week longer of possible ammonia emissions. You also see that coming back. A lower stocking density means that you have an increased manure surface area per bird, because your house is the same size. You just have a reduced number of birds, but ammonia emissions is equivalent to the surface area of your litter. And yeah, maybe there are also some other causes. One of the things that also checked out was the feed composition. The slow growing birds also got a different feed. Actually, they got reduced protein intake of 1% reduction. It's also there that even though they get the reduced feed in protein intake, they even got a higher ammonia emission. So it was also quite strange. Now to summarize, there are some results there. Is that we saw on production, we saw the slow growing chicks, for instance, they had a higher feed intake and a worse food conversion. On welfare measures, we saw that the slow growing birds were actually scoring better, less foot pad lesions, more active, better gate scoring. So there were definitely some benefits in that on that purpose. That's also one of the reasons why they want to introduce it. But if we then look at the ammonia emissions, yeah, you got a different perspective. There you see that we even have 2 to 3 times higher ammonia emissions with this slow growing chicks at lower stocking densities. So to conclude this talk, what are the take-home messages I want to give you is that we at the Experimental Poultry Centre are fully equipped to do future ammonia emission trials in layers and broilers. So we have different setups. We can measure different and even more measures and techniques in our poultry shed. Another thing is that the application of new animal welfare standards, they seem to have a high environmental impact. So we need to consider that before we take a decision to implement it in the sector. The farmers, there's a great need within them for solutions to control ammonia emissions, because they know they have to reduce it in future. So, but the amount of solutions is still very limited. So we are in dire need of more solutions there. And we also need a better understanding of the ammonia emission management. So we know there are options to manage it, but we need to know more and better how to do it. In order to do that, we need to measure more. And if we can measure, you can monitor and then you can manage it. So with the sensors that are available, we take a start there, but we still need a lot to learn. And what we also see, we see this trend mainly in the Netherlands. What I showed you here is that we, of the government, proposed here a predefined list of measures, whereas in the Netherlands, they want to move more to emission target level for each farm, so that you get a target level. This is your threshold. You can do whatever you want, just don't go over your threshold. But in order to manage that, you need to measure it on farm, on every farm. So that's something we still have to develop and further research in the future. So by this, I want to conclude my talk. If you have any questions, you can ask them now. But if you have some questions afterwards, I put my email address here, so you can send me an email, and hopefully we can see each other in the near future then. Thank you very much.
Thank you, Tom, for your presentation. Yeah, we have a question from the audience. We have Hector Leiva. He say, hello, when having automated sensors is not possible to monitor ammonia, handheld devices, tubes, or test papers are used. However, they can be highly affected by a lot of factors, which creates a lot of variability. Would you have any recommendation when using this device to reduce variability in the field?
Yeah, it's correct that there's a lot of variability also with the automatic measures there, or automatic sensors. There can be some variability. For instance, the location of the sensor is very important. We chose to install our sensors at the exhaust fan because we want to measure the emissions. So we want to know what's going out of the house. If you put the sensor, for instance, in the middle of the compartment, you probably get different readings of the concentrations. So the location of the sensor is quite important. The question was about the tubes, test tubes that you can use. I think they can be useful, but that only gives you like a snapshot of the situation. It's not for continuous measurement. It can only give you an indication of the level in the house like it is. What we want to do is to get an almost real-time overview of the emissions. So that's why we want to work with automated sensors so we can measure time after time continuously in the compartments. And then you can study the effects of the management practices that you take.
Okay, so thank you very much. I think that we don't have more questions for the audience. Again, Tom, thank you very much for your presentation and very nice work that you guys are doing in the center. We have two more webinars to go in collaboration with the Experimental Center. So again, this will be accessible in maybe 1 week and a half. And thank you and see you in the next time, Tom. Thank you very much.
Yeah, thank you for the invitation.
Bye-bye. Ciao.
Bye.